This is your presenter, Asloop Mudassar, and I am presenting slide number 13D of the course on atomic and molecular physics. In the today's lecture, I shall be covering push and back effect and splitting of states under push and back effect. Before that, I have discussed ordinary Zeeman effect and anomalous Zeeman effect in the previous lectures. So this lecture is also in the continuation of the previous lectures. So push and back effect. Splitting under weak magnetic field B naught, where B naught is smaller. So the splitting under weak magnetic field is smaller when compared with fine structure splitting or the spin orbit splitting. Or in other words, the spin orbit coupling, which is we call as LS coupling, is stronger than the coupling between the spin angular momentum and the applied magnetic field, or the coupling between the orbital angular momentum and the applied magnetic field. So here we are considering the point that if the magnetic field, applied magnetic field is weak, then the splitting of states will be smaller in compared with the splitting of states which is achieved under fine structure, that is which is achieved under the coupling between the spin and orbits coupling. And you know that when we talk about the spin orbit coupling, it is referred to as the LS coupling. And the spin orbit coupling is stronger than this coupling, which is the spin and magnetic field coupling, or the orbital and the magnetic field coupling. So you see that here I have mentioned the coupling between the spin angular momentum and the magnetic moment, and also the the coupling between the orbital angular momentum and the magnetic moment. In principle, you know that from the previous lectures we have learned that actually there is a coupling between the spin magnetic moment mu s and the applied magnetic field p naught. And similarly, there could be a coupling between the orbital magnetic moment, which we designate as mu l, and B naught. So that will be the true coupling between the magnetic moments and the applied magnetic field. So you see that when we discussed the weak magnetic field, we have discussed two major effects. One was the ordinary Zeeman effect, and the other was the anomalous Zeeman effect. In ordinary Zeeman effect, the spin magnetism was not present and only the orbital magnetism was present. And we have seen that when we talked about the anomalous Zeeman effect, then both the spin magnetism and the orbital magnetism both were present. And you know that in the push and back effect, which we shall be discussing in the next few pages, we are considering the effect under strong magnetic field. And ordinary Zeeman effect and anomalous Zeeman effect were discussed under the weak magnetic field. So this push and back effect is the effect very similar to those of the Zeeman effect, but this effect will be observed only under strong magnetic field. So let's talk about the spin orbit coupling, which we have discussed in equation number 54 of slide number 12. And there we found that VLS, that is the energy splitting between the orbit, due to the coupling between the orbital and the spin magnetism was equal to mu naught over 8 pi times Z square over m naught square into r cube multiplied by the dot product of orbital angular momentum and the spin orbit and the spin magnet and the spin angular momentum as given in equation number 13.42. That is, the spin orbit coupling increases rapidly with increasing nuclear charge Z, because you can see that Z is present in the numerator. So for heavier atom, Z has a larger value, so the value of VLS will be larger for heavier atoms. And if you talk about the lighter atoms, for example, lithium atom, then of course the value of Z is smaller, and then the value of the VLS correspondingly will also be smaller. So the value of VLS will depend upon the value of the Z, or depend upon how much the atom is heavier. So that is why the spin orbit coupling increases rapidly with increasing nuclear charge Z. For heavy atoms, for example, for the sodium D lines, the value of the VLS is of the order of 17.2 centimeter inverse. And for the corresponding lines in the lithium atom, which is a lighter atom in comparison with the sodium atom, the value of the VLS is equal to zero point 0.3 centimeter inverse. So you see that it is very apparent that the value of Z matters a lot, and for sodium atom, its value, the value of VLS is 17.2 centimeter inverse, whereas the same effect for the value for the lithium lines will be equal to 0.3 centimeter inverse. So splitting under weak B naught is comparable with the fine structure splitting for the sodium atoms, like VLS for the lithium atom will be of the order of 0.3 centimeter inverse. And such a splitting can also be observed under weak magnetic field B naught. So the fine structure splitting will be of the same order as that of the splitting observed under weak magnetic field B naught. Stronger field effect can be realized at much lower field values with lighter atoms as compared with heavier atoms. So if we are dealing with the lighter atoms, then of course the condition to meet the strong magnetic field can be realized very easily as compared when we are dealing with the heavy atoms. So stronger B naught dissolves Fs splitting. So you see that when we are dealing with the stronger value of applied magnetic field B naught, then of course the Fs splitting is dissolved. That is, L and S becomes uncoupled. So the coupling, which is normally occurs with the in the LS coupling, in the Fs splitting, or in the LS coupling technique, is broken down in the presence of the strong magnetic field. So L and S becomes uncoupled and precess independently about B naught. So J loses its meaning because L and S will precess independently about the magnetic field B naught. They will not combine to form the total value of angular momentum J. So it means that J loses its meaning, or J will not be talked about, or J is absent. This limiting case is called the Paschen back effect. So you see that in the Paschen back effect, we apply stronger magnetic field B naught. L and S becomes uncoupled. That is L and S, that is this orbital angular momentum, and the spin angular momentum starts their precessional motion about the applied magnetic B naught. And there are other quantities, that is the orbital magnetic moment mu L and the spin magnetic moment mu S will start their precessional motion about the negative direction of the magnetic field B naught. So under that condition, we shall not talk about the total angular momentum J or the total magnetic moment mu of the atom. So such as a limiting a case is referred to as the Paschen back effect. So the Z component of mu L, which we refer to as mu Lz, and the Z component of the spin magnetic moment, which we refer to as the mu Sz, are individually quantized. The corresponding magnetic energy is given by the sum of the magnetic energy due to these two components. So VMLMS, that is the magnetic energy due to the orbital thing and due to the spin thing, that is due to the orbital magnetic quantum number and due to the spin magnetic moment, is given by the sum of these two quantities, that is the sum of GL mu BML B naught and the GS mu BMS and B naught, where ML is the orbital magnetic moment, orbital quantum number, and ms is the spin quantum number. And you know that the rest of the quantities are the same, and this is, we have also spoken about these quantities in previous lectures. So the common things are mu b and b naught are the common quantities. We can take them common out of the two terms, and the two terms in the brackets will be equal to GL ML plus GS and MS, and outside that parenthesis we have mu b and b naught. Here mu b is the Bohr magneton, MS is the spin quantum number, ML is the orbital quantum number, GL is the Lange G factor due to orbital magnetism, and GS is the orbit or GS is the Lange G factor due to spin magnetism. Now you see that the value of GL, the classical value of GL is equal to 1. So we have used its value, which is equal to 1, and the classical value of GS is equal to 2, which we have used over here. So the final expression for the VML will be equal to ML plus MS, and this in bracket multiplied by mu B and B naught as shown in equation number 13.43. So you see that this is what we have found, this magnetic potential energy when both mu L and mu S presets independently about the magnetic field B naught, and we need to add their independent energies as we have done in the first step of this equation. So the final equation is what I have shown, that VMLMS will be equal to, within the parentheses we have ML plus 2 times MS multiplied by mu B and B naught. And if you want to calculate the difference of energy between the spectral lines, then that difference of energy is given by delta E, which is equal to delta ML plus 2 times of delta MS, and outside the parentheses we have mu B and B naught. So you see that this is the delta E is actually the energy difference between the spectral lines. And you know that this depends upon the change in the orbital magnetic quantum number ML, and the change in the spin magnetic quantum number delta MS. And now we are going to consider the selection rules for optical transitions. The selection rule is that delta ML is equal to 0 plus minus 1. When delta ML is equal to 0, then such a transition will be referred to as the pi transition. And when delta ML is equal to plus minus 1, the transitions are referred to as the sigma transitions. Pi transitions are those transitions in which the electric field is parallel to the direction of the magnetic field, and sigma transitions are those transitions in which the electric field of the linearly polarized light is perpendicular to the direction of the magnetic field. So while observing this in the transverse direction to the magnetic field, then the pi transition will be linearly polarized, and the sigma transitions will also be linearly polarized. And there is another selection rule about delta ms is equal to 0. So you see that when we want to calculate the energy between the states given by equation number 13.44, we need to use these two selection rules. Delta ML is equal to 0 plus minus 1, and delta MS must be equal to 0. That is, the spin will not change when the transition will occur. So the change in the spin magnetic quantum number will be equal to 0. So we need to consider these two selection rules simultaneously in order to consider the optical selection rules under the application of strong magnetic field, because the push and back effect is applicable only or can only be observed under the application of strong magnetic field, where the quantities, orbital quantities and the spin quantities are independent of each other. They don't couple, and they independently precess about the magnetic field. That is, there are triplet spectral lines allowed by delta ML, similar to the case of ordinary Zeeman effect. You know that in the ordinary Zeeman effect, we observe only three lines, which is called the Zeeman triplet, ordinary Zeeman triplet. And you can similarly observe that delta ML can have three possible values, 0 and plus minus 1. So due to these three values, we shall call them as triplet spectral lines. So in case of Paschen back effect due to delta ML is equal to 0 plus minus 1, we shall observe the triplet. But you know that we have also delta MS is equal to 0. So if delta MS is equal to 0, then of course, depending upon the value of delta MLS, we may observe more than 3. For example, if MS, that is the spin magnetic quantum number, has two values, for example plus half and minus half, then these two values will multiplied with these three values, then the total number of transitions will be 6. And suppose that in some other transitions, if delta ms has, for example, has four values, then of course delta ml has three values, and these three values multiplied by those four values will give you 12 transition lines. But over here in this problem, we shall be considering in the today's lecture, we shall be considering when ms has two values, that is plus half and minus half, and these two values will be multiplied by these three possible values of delta ml, and we shall have six values for the transitions. So if we don't consider delta ms, then of course this will be a triplet lines. So but you see that we have to discuss, we have to consider delta ms also, and then of course the number of lines will be different from the triplet. So now we can consider this figure as shown over here. You see that in this figure I have shown capital S as the spin angular momentum, that is the total spin angular momentum of the atom, and you see that the tip of this spin angular momentum precesses precessional motion about the loop which is shown in green color, and this capital S vector will precess about with its tip about the magnetic field B naught, and you know that this capital S vector, which is the spin angular momentum, will have three components, Sx, Sy and Sz. So the Sx component and Sy component, they will be averaged to zero due to their precessional motion about the magnetic field B naught, and only one component Sz, which is the Z component of the spin angular momentum, will survive. And similarly, you can see the angular momentum L. The orbital angular momentum L will carry out its precessional motion about the magnetic field with its tip which is tracing the loop, red loop. So angular momentum L will carry out a precessional loop with its tip following the red loop about the magnetic field B naught. Similarly, the angular momentum L will have three components, Lx, Ly and Lz. The two components Lx and Ly will be averaged to zero, and only the Z component, which is Lz, will survive, and which is what I have shown over here. So the direction of B naught is the same as the direction as the Z direction, and I have not shown, you see that in this diagram, mu s, which is the spin magnetic moment, and mu l, which is the orbital magnetic moment, have not been shown in this diagram. Of course, you see that those magnetic moments, that is the spin magnetic moment mu s, is always anti-parallel to the spin angular momentum. Similarly, the orbital magnetic moment mu l is anti-parallel to the orbital quantum number L, and so that will also be anti-parallel to each other, and they will also precess about the minus B naught direction, and those quantities I have not shown in this diagram. I have shown only the total spin angular momentum S and the total orbital angular momentum L, and I have shown their loops in which they will carry out their precessional motion, that is the green loop and the red loops, and I have also shown their Z components. So Paschen back effect. In the limiting case of strong magnetic field B naught, capital S and capital L precess independently about B naught, and their Z components, which is SZ and LZ, align independently with B naught. that is the S and L components will be independent. And I have shown there in the diagram their precessional motion. In case of strong magnetic field B naught and as applicable to the push and back effect, the total angular momentum J and their corresponding magnetic moment mu J are not defined. So you see that since S and L in this figure, as I have shown you, will precess independently about the magnetic field B naught. It means that the total spin angular momentum and the total orbital angular momentum of the atom or of the electron will not couple in this diagram. So when they will not couple, then of course, then they will not add up together and they will precess independently. So we cannot talk about the total angular momentum J and its corresponding quantity, which is the total magnetic moment of the atom. We shall not talk about these two quantities. The region of weak and strong magnetic fields are difficult to work out both theoretically and experimentally. So it is difficult to determine the region for the weak magnetic field and the region and for the strong magnetic field. That is, we cannot precisely determine the boundary between the weak and the strong magnetic fields. So one electron system, we use small alphabets, that is small j, small l, and small s are used when we are talking about a system having only one electron. But for many electron system, we use capital quantities, that is capital J, capital L, and capital S are used. And you see that I have shown capital L and capital S in this diagram to have a more generalized picture, which is also applicable to the single electron case and also the cases when more than one electrons are present in an atom. Like Zeeman effect, Paschen back effect, which is PBE, is chiefly used in empirical term analysis. So you see that when we obtain a spectrum, then of course that spectrum can be empirically analyzed using the Paschen back effect, like the case we used the Zeeman effect to analyze the empirical terms in the analysis of the spectrum. In Paschen back effect, one observes only unshifted component, which is the pi component, and two symmetrically split lines, which are called sigma lines, as in the case of ordinary Zeeman effect. So similarly, in Paschen back effect, we observe pi lines and the sigma lines, which we shall see in the next few slides. Now you see that here I am going to discuss the splitting of the Paschen back effect. You see that I have shown over here PBE stands for the Paschen back effect, ML, which is the which is the orbital magnetic quantum number ML, and MS is the spin magnetic quantum number MS. And you see that I am going to show you the splitting between 2p 3 half states to the ground state, which is a 2s half state, and from 2p half state to the 2s half states. Actually, these are the lines corresponding to the sodium lines. So sodium D1 line transition occurs from the transition from P1 half to 2S1 half, and the sodium D2 line occurs under the transition from 2P3 half to the ground state 2S half. And you see that the two lines that I have shown, one is the red line, which shows the transition under the state from 2P3 half to the ground state, which is the 2s half, and there is a green transition from the 2p1 half to the 2s1 half, which corresponds to the sodium D1 line, and the red line corresponds to the sodium D2 line. And you know that when we don't talk, if we don't have the magnetic field, then of course these two lines are observed only. Sodium D1 line shown in green and sodium D2 line, the sodium D2 line shown in red under the selection rule of delta L is equal to plus minus 1. But when you apply a strong magnetic field, then of course the Paschen back effect is observed. That is, these splitting will observe as I have shown over here. For example, these are the splittings under push and back effect on the right side of this. But to explain that one, how we obtain these splitting, so let me consider 2p3 half state and 2p1 half state. For these two states, that is for 2p3 half and 2p1 half states, I have the value of capital L is equal to 1. And you know that since in the sodium atom, the valence electron has only one electron, so we have capital S is equal to half for the case of single electron. And you know that when capital L is equal to 1, the orbital magnetic quantum number will have three values, 0, plus, minus 1. And when capital S is equal to half, the spin magnetic quantum number will have two values, plus, minus half. So for these two states, that is for 2p3 half and for the 2p1 half states, we have these values, three values of ml, which is equal to 0, plus, minus 1, and two values of ms is equal to plus, minus half. So if you multiply these two values of ms to the three values of ml, then you get 6 in the number. So it means that there will be total 6 transitions for these values. And you know that I have shown the ml values over here. ML values, three values. But you know that with these three values, and since there are two values of ML plus, so with the plus 1/2, there will be three values of ML, and for MS is equal to minus 1/2, there will be three values of ML. So for plus half values of MS, there will be three values of ML, which I have shown over here. So MS is equal to plus half, MS is equal to plus half, MS is equal to plus half. So for plus half values of MS, there are three values of ML, plus 1, 0, and minus 1. And similarly, for minus 1/2 value of MS, which I have shown in green, there are three values of ML, plus 1, 0, and minus 1. Okay, so let me now explain the ground state of the sodium atom. You know that the ground state is 2s half, and for this state, because for capital S we have L is equal to 0, and since we are discussing the sodium atom in its ground state, which has only one electron there, so the capital S will be equal to half. So capital L is equal to the orbital quantum number, which is L is equal to 0, and capital S is the spin quantum number, which is S is equal to half. And their corresponding magnetic quantum numbers will, ML will be equal to 0. When L is equal to 0, ML is equal to 0. When S is equal to half, MS is equal to plus, minus half. So two values of MS and one values of ML is equal to 0. So in total, there will be only two values. So you see that I have shown the red value of plus half and the 0 value of ML. Similarly, I have shown minus 1/2 value in green for the MS value and 0 value for the ML for the ground state. The separation between the levels in the ground state is higher in comparison. So you can see this separation between the two levels of the ground state with ML is equal to 0. And other values are also shown. So let me explain the other values. So you see that there are total six values. So P3 half will have 6 values. Sorry, P3 half and P1 half, these two terms together will have 6 values. And these 6 values are for each plus MS value, there will be 3 values of ML. And for minus half value of MS shown in green, there will be correspondingly 3 values of ML. So these are actually six splittings. So I have drawn some splittings from P3 half. So this is the splitting. You see that corresponding to ML is equal to plus 1, then ML is equal to 0, and I have also drawn M is equal to minus 1 from the P3 half, and I have also drawn another term corresponding to ML is equal to minus 1 and MS minus half, and ML is minus 1, And I have drawn two terms from P1 half, one corresponding to ML is equal to 0, the other corresponding to ML is equal to plus 1. So you see that in principle, I should not designate, I should not point out these six values, four values linked to P3 half and only two values linked to P1 half. These linkages have been shown only for the case when we shall compare the Paschen back effect with the anomalous Zeeman effect. Otherwise, there is no need to connect these values, four values with P3, four splittings with P3 half and two splittings with P1 half. So forget about for the time being with their association with these P3 half and P1 half. Only concentrate that there are six values, six splittings. Three splittings of ML corresponding to each value of MS shown in red and another values of MS value shown in green, and there are corresponding three values of ML. So these are the six values. And experimentally, we have found for these sodium D lines and the splitting of the sodium D lines under strong magnetic field that the separation of these lines will satisfy this condition. And we have drawn these separations for this is the actual spectrum that we have measured from by the splitting of the sodium D lines under strong magnetic field. So this is the spectrum that has been observed experimentally, and we have labeled these ML values and MS value to those values in the Paschen back effect. And the ground state, which has two levels, has also been labeled and has been explained under strong magnetic field. So you see that now I have shown the splitting. The red lines you can see, two red lines has been shown, and these two red lines will satisfy the condition that delta ML will change by +1. So you can see that these, for example, this one will start ML is equal to +1, and the other end of that one joins to the ground state, because we have to carry out all these transition from the higher states to the ground state, because in the ground state we have only two levels. So you see that this plus ML is equal to +1 joins with the ground 0 of the ground state. It means that ML is equal to +1. Similarly, we have joined the other term for which the delta ML is equal to +1 with the +1 value of ML and 0 value of ML in the ground state. The second red line starting from +1, ML is equal to +1 to the ML is equal to 0. So for these two red lines, the delta ML is equal to +1. I have drawn the two green lines, and for these two green lines, the value of delta ML is equal to 0 is satisfied. For example, the top green line starts from ML is equal to 0 and its bottom connects to the 0, ML is equal to 0 of the ground level. Similarly, the other green level starts from ML is equal to 0 and connects to the ground level of ML is equal to 0. So you see that here these two green lines show you the transition under which the delta ML change by 0. The other two light brown transitions have also been shown, and you can see that for these one the delta ML is equal to -1, because here you have shown that the transition starts from delta ML is equal to -1 to the 0 value of the ML in the ground state, and the second starts from delta ML is equal to -1 to the ground state. So delta ML is equal to will be the change in delta ML is equal to -1. Okay, these are the six lines. But you know that for these six lines, the splittings are such that only three wavelengths will be emitted. That is, only three wavelengths are observed out of these six splittings. So that is the two shown in the red will have single wavelength, the two shown in green will have the single wavelength, and the two shown in the light brown will have the single wavelengths. The green ones will be referred to as the pi transitions. All these transitions, when measured perpendicular to the direction of the magnetic field, will be linearly polarized. So this is the pi linearly polarized light due to the green transitions, in which the electric field of the linearly polarized light is perpendicular to the direction of the applied magnetic field. Sorry, parallel to the direction of the applied magnetic field. And for the two sigma lines, for one sigma lines, the transition is delta ML is equal to +1. For the other sigma lines, the delta ML is equal to -1. For these two transitions, which are referred to as the sigma plus or the sigma minus transitions, the wavelength for these two transitions will be different, but for the red transitions we have the same wavelength. For the light brown transitions we have the same wavelengths, and these are respectively called sigma plus and sigma minus. Both these transitions are linearly polarized, but in these two transitions the value of the electric field is perpendicular to the direction of the magnetic field. So you see that these are actually the triplet lines. So the Paschen back effect can be said to have the triple lines, similar to the case of the ordinary Zeeman effect, because we observe only three lines over there in case of a Paschen back effect. So the Paschen back effect may be considered to be very much similar to that of the ordinary Zeeman effect. And one thing that I have shown its connection with these levels is just for the case when we compare the Paschen back effect with the anomalous Zeeman effect, which we shall present in the next slide. Otherwise, there is no need to show these connections. But remember that these two excited states, which are P3 half and P1 half, these two together will produce 6 lines. And this is what I have shown, 6 lines by using the combination of ML and MS. That is, for each value of MS, there are 3 values of ML. So 6 lines are formed. And for the ground states, only 2 lines are formed, because the 2 values of MS are possible, but only one value of ML is there. So only 2 lines will be formed. So you see that now I have explained the spectrum that was obtained under the application of strong magnetic field when applied to the sodium atom, and we observed the push and back effect. And we also observed the triplet lines, which may be referred to as the push and back triplet. Now you see that in the next slide, I am going to make its comparison, that is the comparison of the push and back effect with those of the anomalous Zeeman effect for the case of sodium D1 line and sodium D2 lines. So you see that I have shown the sodium D1 line and sodium D2 line actually for the transition from 2p1 half to 2s1 half, and for the transition from 2p3 half to 2s1 half, which is the sodium D2 line. And you know that in the case of anomalous Zeeman effect, you apply moderate value of a magnetic field, in which the J values or the J value is split into MJ values. That is the J degeneracy, which is a one level, 3 by 2 is one level with J degeneracy, will be split into 4 levels of Mg levels. That is, the degeneracy is lifted when you apply moderate magnetic field, as in case of anomalous Zeeman effect. So the values of Mg will be equal to plus minus 3 by 2 and plus minus half. And similarly, for the case of a P1 half, the degenerate level, which is J is equal to 1 half, this J degeneracy will be lifted into 2 levels. Mg is equal to plus minus 1 half under the application of moderate magnetic field, as in case of moderate magnetic field, as in case of anomalous Zeeman effect. Similarly, the level S half will be splitted, the J level in S is equal to 1 half, which is capital J is equal to 1 half, will be splitted. J degeneracy will be lifted, and Mj will have two values, plus half and minus half. And you know that I have shown anomalous Zeeman effect The four lines of this Zeeman effect left to this vertical dotted line in black has been shown. So these are the four anomalous Zeeman effect corresponding to D1 line of the sodium atom. But you know that for the D2 line, which is under the transition of P3 half to the ground state, you will observe the splitting on the right side of this black dotted line. And this is again a anomalous Zeeman effect. And you know that there are a total of 6 lines. So you will observe 6 lines over there. You can see 6 lines on the right of this dotted line and 4 lines on the left of this dotted line. 4 lines correspond to the sodium D1 line under the anomalous Zeeman effect, and these 6 lines which are on the right side of the this dotted black line, these 6 lines are due to the anomalous Zeeman effect, and they correspond to the sodium D2 line under the moderate application, that is under the anomalous Zeeman effect. And you know that I have also shown the push and back effect on the right side of the second dotted line. And this push and back effect is what I have explained in the previous slide in much greater detail. And these linkages, you see that now you can compare these linkages with those of the anomalous Zeeman effect. Because the top there are 4 levels, and I have made their connections with the splittings of the push and back effect lines or the splittings. And similarly, for the ground state, I have connected these with the levels of the anomalous Zeeman effect. So two levels of the Zeeman effect, which are mg is equal to plus minus half, they will appear as two lines again of the push and back effect. So together we have 6 lines of P1 half and P3 half as shown for the case of the push and back effect. And there I have tried to correlate the 4 splittings of the push and back effect with the 4 values of the mj values for the case of anomalous Zeeman effect. And then I have tried to connect the other 2 values with the second level of the P half levels, where mj has 2 values. So the six values of the mj values, 4 values are plus minus 3 half and plus minus half, plus minus 1 half, and other 2 half and the other 2 values are mj is equal to plus minus half. These 6 values have been correlated with the 6 values of the push back effect and have been explained in detail. So the similarity is that push and back effect is quite different from the anomalous Zeeman effect, but the lines in the push and back effect is a triplet, which is much similar to that of the ordinary Zeeman effect, and I have not shown the ordinary Zeeman effect in this diagram. So you see that in the today's lecture, I have explained the push and back effect in much greater detail. So this lecture is continued to the next case in which, and you know that these are the lectures in which we are applying the magnetic field, external magnetic field to the atom. In the first case, we discussed the effect which was the ordinary Zeeman effect. Then we discussed the anomalous Zeeman effect, and today we discussed the push and back effect. And in the next slide, we shall discuss the double resonance method. So now it is the end of slide number 13D of the course on atomic and molecular physics. And the lecture is continued.